What if humanity's first contact with alien technology already happened, and we almost missed it? In October 2017, a mysterious cigar-shaped object from deep space blazed through our solar system at 87.71 kilometers per second, faster than any natural object should move. Scientists called it Oumuamua, meaning scout from afar. But here's the kicker: this thing accelerated away from the sun without any visible propulsion, breaking every law of physics we know. Did you know that some Harvard scientists seriously believe we just witnessed our first alien spacecraft? Oumuamua initial detection. On October 19, 2017, the cosmos delivered humanity its first confirmed interstellar visitor, and Robert Warwick at the Pan-STARRS, one telescope in Hawaii, was the lucky astronomer to spot it first. But this wasn't your typical space rock discovery. Oumuamua was already 33 million kilometers away from Earth when we finally noticed it, traveling at speeds that, honestly, just screamed alien highway. The object had performed its closest solar flyby on September 9, 2017, coming within 38 million kilometers of our sun before we even knew it existed. Its hyperbolic trajectory told an incredible story. This visitor had traveled through the dark void between stars for potentially millions of years before stumbling into our cosmic neighborhood. The Hawaiian name Oumuamua means scout or messenger from afar arriving first, and boy did it live up to that name. What made this discovery earth-shattering wasn't just its interstellar origin. It was moving too fast for our sun's gravity to capture it permanently, meaning we had only a brief window to study this cosmic time capsule before it vanished back into the infinite darkness between stars. The detection itself was almost miraculous timing. Oumuamua was already on its way out of our solar system when spotted, having reached its perihelion weeks earlier. The astronomical community immediately recognized this as a once-in-a-lifetime opportunity to study pristine material from another star system, triggering an unprecedented international observational campaign. Within days of discovery, telescopes worldwide were trained on this mysterious visitor, desperate to gather as much data as possible before it faded beyond detection limits forever. Classification challenges. Scientists love putting things in neat categories, but Oumuamua laughed in the face of their organizational systems. Initially tagged as Comet C-2017-U1 due to its hyperbolic escape trajectory, astronomers expected to find the telltale fuzzy coma that forms when comets heat up near the sun. Instead, they found absolutely nothing: no gas, no dust, no glowing halo whatsoever. This forced an immediate reclassification to asteroid A2017-U1, but even that didn't stick. Once confirmed as definitively interstellar in origin, it earned the historic designation 1I-2017-U1, literally the first official member of an entirely new category, interstellar objects. This classification nightmare reflected something deeper and more unsettling. Oumuamua didn't behave like any known comet or asteroid in our solar system. It was forcing scientists to create new categories because existing ones simply couldn't contain its strangeness. The International Astronomical Union had to scramble to establish naming conventions for objects that, until 2017, existed only in theoretical papers. This classification chaos was just the beginning of Oumuamua's assault on conventional astronomical wisdom, setting the stage for discoveries that would challenge everything we thought we knew about how objects behave in space. The unprecedented situation required emergency sessions among astronomical organizations to establish proper nomenclature protocols. Minor Planet Center Director Gareth Williams worked around the clock to coordinate the classification process, while researchers debated whether traditional comet-asteroid distinctions even applied to interstellar visitors. The object's refusal to fit existing categories forced a fundamental reimagining of how we classify celestial bodies, acknowledging that our solar system's objects might represent just a tiny fraction of the diversity that exists in interstellar space. Trajectory analysis. When Oumuamua entered our solar system, it didn't follow any ordinary orbital mechanics playbook. This interstellar intruder approached from north of the ecliptic plane at an extreme angle, suggesting it originated from the direction of the bright star Vega in the constellation Lyra. As it screamed toward the sun, Oumuamua accelerated to an absolutely mind-bending 87.71 kilometers per second, fast enough to circle Earth's equator in just over 7 minutes. The sun's immense gravitational field acted like a cosmic slingshot, bending the object's trajectory into a sharp northward curve during its closest approach at 0.255 astronomical units, approximately 17% closer to the Sun than Mercury ever ventures. This gravitational dance launched Oumuamua on an escape trajectory toward the constellation Pegasus, ensuring it would leave our solar system forever. But here's what made trajectory analysts lose sleep. The object's path showed subtle deviations that couldn't be explained by gravitational forces alone. These tiny but measurable course corrections suggested something was pushing Oumuamua in ways that defied Newton's laws. The trajectory data painted a picture of an object under the influence of mysterious forces that would later become the center of heated scientific debates about alien technology versus exotic natural phenomena. Detailed orbital calculations revealed that Oumuamua had likely been wandering through interstellar space for hundreds of millions of years before its chance encounter with our solar system. The object's orbital eccentricity of approximately 1.2 marked it as definitively unbound to our Sun, while its inclination of about 122 degrees indicated it was traveling nearly perpendicular to the plane of our solar system. NASA's Jet Propulsion Laboratory continuously refined trajectory predictions as new observations poured in, but the mounting evidence of non-gravitational forces would soon turn routine orbital mechanics into one of astronomy's greatest puzzles. Photometry and shape analysis. Nothing had prepared astronomers for Oumuamua's absolutely bizarre light curve behavior. As this cosmic enigma tumbled through space with a 7.3-hour rotation period, its brightness varied by an unprecedented factor of 10, meaning it alternated between being 10 times brighter and 10 times dimmer as it spun. No known asteroid or comet in our entire solar system exhibits such extreme brightness variations. The only way to explain this dramatic light show was if Oumuamua possessed an incredibly elongated shape, possibly 10 times longer than it was wide, resembling a cosmic cigar or needle. Some models suggested even more exotic geometries, with dimensions potentially reaching 240 meters wide by 1,080 meters long, or alternatively, a pancake-shaped object of similar proportions. The Spitzer Space Telescope observations provided crucial constraints, indicating the object's surface was surprisingly reflective, about 4 times more reflective than typical asteroids. This high albedo suggested either an unusual composition or a surface coating of some kind. The extreme aspect ratio challenged everything scientists understood about how celestial bodies form and evolve. Natural processes typically create relatively spherical objects due to gravitational forces, yet Oumuamua appeared to violate these fundamental principles. Its shape was so unusual that some researchers began seriously considering whether natural formation processes could even produce such an object, opening the door to more exotic explanations. Acceleration anomaly. June 27, 2018 marked the day that Oumuamua officially broke physics, or at least appeared to. Marco Michelli and his team published observations showing that this interstellar visitor was accelerating away from the Sun in a way that gravity alone couldn't explain. The non-gravitational acceleration was subtle but undeniable, changing the object's velocity by approximately 17 meters per second over the observation period. For any normal comet, this would be easily explained by outgassing, when solar heat vaporizes ice, creating jets that act like tiny rocket engines. But Oumuamua had already proven it wasn't normal by showing zero signs of a coma or tail. The acceleration was detected through precise astrometric measurements that tracked the object's position against background stars with incredible accuracy. The force appeared to be acting radially away from the Sun, similar to solar radiation pressure, but Oumuamua would need to be impossibly lightweight or have an impossibly large surface area for photons alone to push it around. This discovery sent shockwaves through the astronomical community because it suggested either exotic physics or exotic origins. The acceleration magnitude was tiny, about 5 times 10 to the minus 6th meters per second squared, but measurable enough to rule out observational error. Scientists found themselves facing an object that was simultaneously too dense for radiation pressure and too inactive for typical cometary outgassing, creating a perfect storm of confusion. Spitzer observations. The Spitzer Space Telescope became humanity's detective in the case of the missing Oumuamua. During November 2017, This infrared space observatory stared at the object's predicted location for over 30 continuous hours, searching for any thermal emission that would reveal its true size and composition. The result? Absolutely nothing. This non-detection wasn't a failure, it was actually a goldmine of information that deepened the mystery exponentially. Spitzer's inability to see Oumuamua placed strict upper limits on the object's thermal emission, which in turn constrained its size to no larger than 440 meters in its longest dimension, assuming typical asteroid-like properties. More importantly, the lack of detectable heat signature ruled out significant amounts of carbon monoxide, carbon dioxide, and dust production, the typical calling cards of active comets. This observation was crucial because it eliminated many conventional explanations for the mysterious acceleration. If Oumuamua wasn't producing detectable amounts of gas or dust, then what invisible force was pushing it around? The Spitzer data also suggested the object's surface temperature was consistent with a dark, possibly organic-rich composition, similar to the outer solar system objects. Yet this composition didn't match the high reflectivity observed at visible wavelengths, creating another layer of contradiction. The telescope's failure to detect the object directly contributed to size estimates and ruled out many exotic composition theories, but it also eliminated easy explanations for the acceleration anomaly, pushing scientists toward increasingly creative theoretical solutions. Artificial origin hypothesis. Abraham Avi Loeb, Harvard's controversial astrophysicist, dropped a bombshell that sent ripples through both scientific circles and popular media. In his 2018 paper and subsequent 2021 book Extraterrestrial, Loeb argued that Oumuamua's unique characteristics, its extreme elongated shape, unusual reflectivity and mysterious acceleration, could only be satisfactorily explained if it were an artificial object created by an alien civilization. Specifically, Loeb proposed that Oumuamua might be a light sail, which is, an ultra-thin sheet of material designed to be pushed by stellar radiation for interstellar travel. This technology, while still theoretical for humans, could explain both the object's extreme thinness, giving it that unusual aspect ratio, and its acceleration away from the sun via solar radiation pressure. The hypothesis suggested we might have witnessed discarded alien technology or even an active probe sent to investigate our solar system. Loeb's argument wasn't based on wild speculation but on systematic elimination of conventional explanations. He calculated that for solar radiation pressure to account for the observed acceleration, Oumuamua would need to be incredibly thin, perhaps only millimeters thick, which could occur naturally only under the most extraordinary circumstances. The artificial origin hypothesis sparked fierce debate, with most astronomers maintaining that extraordinary claims require extraordinary evidence. However, Loeb's rigorous mathematical approach forced the scientific community to seriously consider possibilities that had previously been relegated to science fiction, fundamentally changing how we approach anomalous observations. Dark comet theory. Enter the dark comet theory, the scientific community's attempt to rescue Oumuamua from alien conspiracy theories while still explaining its impossible behavior. Alan Fitzsimmons and his colleagues proposed that Oumuamua represents a new class of object comets that have been so heavily processed by cosmic radiation and interstellar weathering that they've lost their ability to produce visible comas and tails. The theory suggests that during its millions-year journey through interstellar space, Oumuamua was bombarded by high-energy particles that altered its surface composition and internal structure. This processing could have created a carbonaceous crust that insulates the interior while still allowing subtle outgassing of invisible materials like hydrogen gas. In 2023, Jennifer Bergner and Daryl Seligman published groundbreaking research showing that cosmic ray bombardment of water ice can produce trapped molecular hydrogen that later escapes when heated by the sun. This hydrogen outgassing would be completely invisible to telescopes, but could generate enough force to explain the observed acceleration. The beauty of this theory is that it explains not just the acceleration anomaly, but also why Oumuamua appeared so different from familiar comets. The dark comet model suggests that interstellar space is filled with these ghostly, processed remnants of ancient planetary systems, objects that look dead but retain just enough activity to push themselves around when they encounter a star's heat and light. Dark comet classification. The dark comet classification emerged as astronomers realized that Oumuamua might not be unique, but rather the first detected member of an entirely new category of celestial objects. These dark comets are defined as objects that exhibit non-gravitational acceleration, the smoking gun of outgassing activity, without displaying any visible signs of cometary behavior like comas, tails, or dust production. The classification system divides these mysterious objects into categories based on their size and orbital characteristics. Large dark comets like Oumuamua follow hyperbolic trajectories and likely originate from interstellar space, while small dark comets remain gravitationally bound within our solar system. Recent discoveries have identified several potential dark comet candidates within our own solar system, including objects like 2003 RM and 2005 VL1, which show subtle acceleration signatures without obvious cometary activity. The classification represents a fundamental shift in how astronomers categorize solar system objects, acknowledging that the traditional asteroid-comet dichotomy is insufficient to describe the full diversity of objects in space. Dark comets challenge our understanding of planetary formation and evolution, suggesting that the boundaries between different types of celestial bodies are far more fluid than previously believed. This new classification system also has profound implications for planetary defense strategies, as dark comets might be more difficult to detect and track than traditional objects, yet their unpredictable acceleration could alter their trajectories in unexpected ways. Scientific debate. The scientific community remains locked in a fascinating intellectual battle over Oumuamua's true nature, with competing theories each addressing some aspects of the mystery, while leaving others unexplained. The mainstream scientific consensus, established by July 2019, favors natural explanations, with the hydrogen outgassing model gaining significant support following Bergner and Seligman's 2023 research. This theory elegantly explains both the acceleration and the lack of visible outgassing through cosmic ray processing of interstellar ice. However, alternative explanations persist, including nitrogen ice composition models proposed by Alan Jackson and Stephen Desch, which suggest Oumuamua might be a fragment of a Pluto-like exoplanet. The artificial origin hypothesis championed by Avi Loeb continues to attract attention despite mainstream rejection, particularly given the lack of definitive proof for any natural explanation. Some researchers propose even more exotic scenarios, including dust bunny models where Oumuamua could be an extremely low-density aggregate held together by electrostatic forces. The debate has highlighted crucial gaps in our understanding of interstellar object formation and evolution. The upcoming Vera Rubin Observatory, scheduled to begin full operations in the mid-2020s, promises to detect hundreds or thousands of similar objects, potentially providing the statistical sample needed to resolve the debate. Meanwhile, ESA's proposed Comet Interceptor mission could potentially visit another interstellar visitor if one arrives at the right time. The scientific controversy surrounding Oumuamua has already advanced our understanding of solar system formation, interstellar space conditions, and the importance of rapid response observations for transient celestial phenomena, regardless of which theory ultimately proves correct. That's the incredible story of Oumuamua, our first confirmed interstellar visitor that continues to challenge everything we thought we knew about space. From its mysterious acceleration to its impossible shape, this cosmic enigma proves that the universe still holds secrets we're only beginning to understand. What do you think Oumuamua really was? Natural phenomenon or something more extraordinary? Drop your theories in the comments below. I'd love to hear your thoughts. If you enjoyed diving into this cosmic mystery, hit that subscribe button and ring the bell icon to never miss another mind-bending episode from Simply Science. Until next time, keep looking up.